Hello students, I thought we could use a little change of pace. So I went on to Nextdoor and I found someone who was giving away a chalkboard for free. I took the chalkboard back to my office at home and now I have this studio at home where I can share more mathematical content with you. So I'm excited to get started. That doesn't mean we're not going to have any more Lightboard videos. We'll still have plenty of Lightboard videos. This is just basically another way we can learn mathematics together and allows me greater flexibility to answer questions in a much more rapid fashion. So let's get started. Today we're going to talk about a special case of the Codazzi-Mainardi equations. And what is this special case? So this special case is the case when the first fundamental form looks like E du squared plus G dv squared. And the second fundamental form looks like L du squared plus N dv squared, okay? In other words, in this special case, we have no middle terms here. So there's no F term and there's no M term in these. And that makes things a little bit easy because we can do the following now. We can write the inverse of the first fundamental form times the second fundamental form is going to be this matrix over here. It's going to be G, 0, 0, and then E, and then L, 0, 0, and then N, all scaled by E over G, which is the determinant of the first fundamental form matrix, okay? What this allows me to do now is this allows me to easily find out what the two principal curvatures are, right? So the principal curvatures now are going to be, if I do this row and this row over here, it's going to be a diagonal matrix. I'm going to have L times G over E times G, so my kappa 1 is going to be what? My kappa 1 is going to be L over E. And my kappa 2, my second principal curvature, is going to be what? Is going to be this over here, so it's going to be an En over Eg. That's going to be an N over G. N over G. And those are our principal curvatures. Great. Now, what do the Codazzi-Mainardi equations reduce to? Well, there's no M terms, and so we get the following. So the Codazzi equations now have the following form. They're going to be an L V is going to be a gamma 1, 1, 2 L minus gamma 2, 1, 1 N. And then negative NU is going to be what? Negative NU is going to be gamma 1, 2, 2 L minus gamma 2, 2, 1 N, like so. So that's what my Codazzi-Mainardi equations reduce to. And so now what can we do? Now we can think about this in the following way. We know what these Christoffel symbols are going to be now, right? So what are these going to turn into? This first thing over here is going to simplify. This is going to look like what? This is going to look like L times what? This thing over here is going to be the V derivative of E over 2E. That's going to be EV over 2E. Minus N times what will this be over here? This is going to be a negative, it's going to be a negative EV over 2G, like that. Excellent. And what will this thing look like over here? This thing over here is going to be what? That's going to be negative, so we have an L, and then a negative GU over 2E. And then this thing over here is going to be a negative N times what quantity? Times the quantity, let's see over here. So this is going to be a gamma 2, 2, 1. So it's going to be a GU over 2G, like that. Excellent. Okay. And so now we get this simplification. So now, of course, what's going to happen is I'm going to factor out. So this tells me, so hence this implies that LV is going to be what? If I pull out an EV over 2, what will happen over here? If I have an EV over 2, then what will happen? EV over 2 and then EV over 2. I'll have an L over E over here, but L over E is K1. That's going to be a K1, kappa 1. plus n over g over here, that's going to be a kappa 2. Beautiful, okay? And then same thing over here. So the next thing we have over here is the following. We're going to have that nu. Now notice everything over here is a negative. Negative, negative, negative. I'm going to get rid of all the negatives. And if I do so, I'll have nu as what? I'm going to pull out a gu over 2. And then I'll be left with what? L over E. L over E is kappa 1. And then plus kappa 2, right? So these are called the reduced Codazzi-Mainardi equations. So these are the reduced Codazzi-Mainardi equations. Excellent. Now what these allow me to do is these allow me to compute the partial derivatives of K1 and K2 in terms of u and v. So let me do that next. So next, consider K1 v, the v derivative of kappa 1, the first principal curvature. Well, let's do it. It's going to be the bottom times the derivative of the top. So that's going to be an E times LV minus the top times the derivative of the bottom, L times EV over the bottom squared. And from this, what I'm going to do is I'm going to factor out a factor of, I'm going to pull out an EV over E. Okay? And if I do that, what's going to happen over here? You might say, why did you do that? Let's check and see what happens over here. So if I pull an EV over E over here, I'm left with negative L over E. So negative L over E is negative kappa 1. So these negative terms over here are going to be negative kappa 1 from these terms over here. So in other words, those terms together, I'll pull out an EV over E. Then I have negative L over E. Negative L over E is negative kappa 1. Now I pull out a what? I pull out a, from these terms, there's only one E in the denominator, so one of the E's cancels out over there. And so I pull out that one over E, but now I have an LV, and I factor out an EV from LV. But what is LV? LV is EV over the average of kappa 1, kappa 2, or the mean curvature, right? So this is going to be plus 1/2 kappa 1 plus kappa 2. And we can simplify this because what we'll do, this is going to be kappa 1, this is going to be kappa 2 over 2, and then minus kappa 1 over 2. So this is going to be EV over 2E. Times what? The kappa 2 is going to be positive and the kappa 1 is going to be negative. So the kappa 2 minus kappa 1, like that. Great. And then finally, what will Ku be? So similarly, if I look at K2 of u, what will that be? K2 of u is going to be bottom times the derivative of the top, so GNU minus GUN over n squared. And by exactly the same algebra, I'm going to factor out an NU. I'm going to factor out an NU over n. If I do so, if I factor out an NU over n over here, I have a G over n, so that's going to be a kappa 2, and then minus the average again. So now the sign flips over here. So this will simplify too. This is going to be GU over 2G, and then kappa 1 minus kappa 2. And these give me partial derivative relationships between these partial derivative relationships for the principal curvatures. Right over here, this is equal to K1V. Will be very, very useful when we're studying surfaces with constant Gaussian curvature and points near umbilical points, points that are umbilical points on the surface. So these two partial derivative equations, when we put the surface into these isothermal coordinates, play an essential role. Thank you very much.